Hello and welcome to today's podcast. This episode is brought to you by Beemit, a trusted manufacturer of precision electrical measuring instruments built for accuracy and safety across industrial and solar applications. Solar energy is one of the fastest growing sectors in the world, and keeping a solar plant running at its best requires more than just good panels and components. It requires precise, consistent measurement of everything happening inside the system, from voltage and current to insulation quality and energy output. In this podcast, we will discuss why accurate electrical measurement is so critical in solar plants, which instruments are used and when, the benefits of getting measurement right, and how to avoid common errors that quietly reduce a plant's efficiency. So let's get started. Let's begin with why accurate measurement matters so much in a solar energy system. The efficiency of a solar plant depends on the quality of its operational data, and that data is only as good as the measurements behind it. Parameters like current and voltage need to be tracked precisely because the system's performance is constantly being influenced by environmental conditions, things that shift throughout the day and across seasons. To put that in context, consider a few specific factors. PV strings in solar plants can operate at anywhere between 1,000 and 1,500 volts DC. At those levels, an inaccurate reading is not just a performance issue. It can cause equipment damage or create a serious safety risk. Solar output also fluctuates with changing light conditions, which means real-time measurement is essential, not optional. Then there's the issue of string imbalance, where mismatched strings quietly reduce overall output, something that only becomes visible when you're actively measuring current and voltage across the system. And finally, inverters must meet power quality standards set by the grid, which requires verifying distortion and flicker through proper measurement tools. Now let's look at the instruments that solar plants actually rely on. The most commonly used tool is the digital multimeter, or DMM. It measures voltage, resistance, and continuity, and is typically used to check panel voltage, wiring, and connections. Alongside it, the clamp meter measures AC and DC current without requiring you to disconnect any wires, which makes it extremely practical for live system checks. For a more detailed look at panel performance, technicians use an IV curve tracer. This instrument traces the current voltage performance curve of a panel and can reveal shading, mismatch issues, or degradation that wouldn't show up in a basic voltage check. To understand how much sunlight is actually available at a site, a pyranometer is used. It measures solar irradiance, the intensity of incoming sunlight, which directly affects how well the system should be performing at any given moment. Cable and system insulation safety is checked using an insulation resistance tester, often called a megger. This is critical both during installation and as part of ongoing maintenance. Thermal imaging cameras add another layer of diagnostic capability. By detecting temperature patterns across panels and connections, they can identify hot spots and loose connections before they become serious faults. Watt meters and power meters track electricity generation and inverter efficiency in real time. Energy meters, on the other hand, record how much energy has been produced or consumed over time, which is essential for net metering and long-term performance tracking. Ground testers verify that the system is properly earthed, which is a fundamental safety requirement. Reference cells measure soiling losses, the power reduction caused by dust and dirt accumulating on panels. And in laboratory settings, solar simulators provide controlled artificial sunlight for testing panels before they go into the field. Finally, data loggers tie everything together by continuously recording multiple system parameters over time. Now, let's understand how these instruments come into play at different stages of a solar project. The first stage is planning. Before a single panel goes up, the site needs to be properly assessed. A pyranometer measures solar irradiance at the location. Solar explorers map shade patterns throughout the year. Solar analyzers measure electrical power potential. All of this data shapes how the system gets designed and sized. The second stage is installation and commissioning. Once panels are up, the system needs to be tested before it goes live. Clamp meters measure current through the strings. Digital voltmeters monitor voltage across wiring. IV curve tracers verify that each panel is functioning as expected. Insulation resistance tests, earth resistance checks, and thermal imaging scans are all carried out to catch any installation issues or safety risks before the system starts generating power. The third stage is ongoing operation and maintenance. This is where long-term performance is either protected or slowly lost. Clamp meters and infrared cameras help technicians find broken strings and developing hot spots. Power quality testers detect harmonic distortion. Reference systems identify energy losses from soiling. Data loggers and energy meters keep a continuous record of how the system is performing over time. Let's talk about what accurate measurement actually delivers in terms of benefits. First, it improves safety. These tools catch problems with wiring and connections early, which significantly reduces the risk of electrical incidents. Second, accurate measurement leads to increased energy generation, because weak or underperforming panels get identified and addressed quickly, rather than quietly dragging down output for months. Third, it ensures compliance. Solar installations have to meet grid and safety standards, and measurement is how you verify that those standards are being met. And fourth, it enables early fault detection, catching shading issues, broken panels, or loose connections before they escalate into something more costly. As we come to the end of this discussion, it's worth understanding what happens when measurement goes wrong. Even small measurement errors can reduce a plant's efficiency in ways that aren't immediately obvious. Using the wrong tool for the job can damage equipment and create safety risks. Improper DC shunts or unstable power references reduce measurement accuracy and, in turn, energy output. Underestimating shading during planning leads to unexpected power loss once the system is running. Harmonic distortion that goes unmeasured can affect inverter performance and component sizing. Dirty panels that aren't being tracked through soiling measurements quietly reduce system efficiency over time. And incorrect voltage measurements combined with temperature fluctuations can result in the wrong repairs being made, which sometimes creates new problems instead of solving existing ones. So choosing the right instruments is just as important as using them. The scale and type of project matters here. A rooftop residential system has different needs from a large utility-scale solar farm. For basic testing and troubleshooting, digital multimeters and clamp meters are often sufficient. But for larger, more complex systems operating at high voltages, you need advanced tools like IV curve tracers and data recorders to measure performance accurately, identify problems reliably, and operate safely. In all cases, accuracy, reliability, and strong insulation performance should be the priority, because these tools protect both the people working on the system and the installation itself. That brings us to the end of today's podcast on electrical measuring instruments for solar plants. From site assessment through to daily operations, the right measurement tools determine how well a solar plant performs, how safely it runs, and how quickly problems get resolved. In solar energy, what you measure is directly connected to what you can improve. Thank you for listening. If you found this episode helpful, please like, share, and subscribe for more informative content. To know more, you can visit our website at beamit.com. Let's wrap it up here. Thanks again for listening.